For nearly 80 years, every computer on this planet has spoken the same simple language. 0 or 1, on or off, yes or no. That two-state code, called binary, is the invisible foundation beneath every phone, every laptop, every satellite, and every artificial intelligence model ever built. But in a quiet laboratory in Beijing, a team of Chinese scientists just did something that could break that 80-year-old rule forever. They built a working chip that does not think in two states. It thinks in three. And if this technology scales the way its creators believe it can, it might not just improve computers, it might replace the entire foundation computing has stood on since the 1940s. Before we go further, if you find stories like this fascinating, take a second to hit like and subscribe, because we cover breakthroughs like this one every single week. So what exactly is a ternary computer? And why does adding just one extra state change everything? To understand that, you have to understand what binary actually is. Every calculation your phone or laptop performs is built from transistors, tiny electronic switches that can only be fully open or fully closed. Open means 1, closed means 0. String billions of these switches together in the right pattern, and you get everything from a text message to a video game to a large language model. It works. It has worked for decades. But it is also incredibly wasteful because two states can only carry so much information before you need more transistors, more wiring, and more electricity to do the same job. Ternary computing changes the rule by adding a third state. Instead of just 0 and 1, a ternary system uses 3 values, often written as -1, 0, and positive 1. That might sound like a small tweak, but mathematically it is enormous. A single ternary digit, sometimes called a trit instead of a bit, can represent more information than a binary digit. In theory, a ternary system needs meaningfully fewer components to represent the same amount of data as a binary one. Fewer components mean less wiring, less wasted energy, and less heat. 3 of the biggest problems facing modern chip makers right now. Here's the twist most people do not know. Ternary computing is not new. It did not start in China, and it did not start in this decade. The very first ternary computer was actually built in the Soviet Union back in 1958 at Moscow State University. It went in S called the Saturn, named after a small river near the university. Soviet engineer Nikolai Brusentsov and his team built it because Soviet factories at the time struggled to produce reliable components for binary machines. The Saturn used roughly 1/3 fewer parts than a comparable binary computer of that era, and it turned out to be strangely elegant at handling certain kinds of arithmetic, including addition and subtraction, without needing extra circuitry that binary machines required. But the Saturn never spread beyond a small number of units. The rest of the world had already standardized around binary logic, largely because the transistor industry built its entire manufacturing base, its entire tool set, and its entire theoretical framework around the idea of two states. Switching an entire global industry to a 3-state system would have meant throwing away decades of infrastructure. So ternary computing became a historical curiosity, a clever idea that lost to convenience. For almost 70 years, it sat quietly in textbooks as a footnote. Only around 50 of these Soviet machines were ever built, and by the mid-1960s, Soviet planners themselves decided to standardize on binary computing, mostly to align with the rest of the world and simplify manufacturing. Brusentsov reportedly continued defending the design for years afterward, arguing that the industry had made the wrong choice for the wrong reasons, choosing convenience over genuine efficiency. For a long time, almost nobody outside of computer science history courses remembered his argument at all. And what makes the current moment strange is that the very problems Brusentsov complained about in the 1950s, wasted components, unnecessary complexity, high and inefficient use of electrical signals, are now the exact problems keeping chip engineers awake at night in 2026. The pressure has simply shifted from manufacturing scarcity in the Soviet Union to raw physical limits and runaway energy demand in the age of artificial intelligence. Fast forward to today, and the conditions that once made binary the obvious winner are starting to break down. Silicon chips are approaching a genuine physical wall. Engineers have spent decades shrinking transistors to fit more of them onto every chip, a trend famously described by Moore's law. But transistors are now so small, some barely a few atoms wide, that engineers are running into the actual limits of physics: heat, power leakage, and interference between. Components are becoming harder and harder to manage. At the same time, the explosion of artificial intelligence has created a new and urgent problem because training and running large AI models consume staggering amounts of electricity, and data centers around the world are straining power grids just to keep up. This is the exact moment when ternary logic, dismissed for 7 decades, suddenly looks very attractive again, and China's researchers appear to have noticed first. In January of this year, a team from Peking University, working alongside researchers from Beijing University of Posts and Telecommunications, published a study in the journal Science Advances, describing a new kind of transistor. Instead of using silicon, their transistor was built from carbon nanotubes, incredibly thin, cylindrical. Structures made from rolled-up sheets of carbon just a single atom thick. Carbon nanotubes have been studied for years because of their unusual electrical properties, but this team did something new. They designed what they call a source gating transistor, which extends the source electrode directly into the transistors, the device to reliably switch between 3 distinct electrical states instead of 2. Using this new transistor design, the team built ternary logic gates, ternary memory cells, and even a small ternary neural network. In their testing, that neural network achieved 100% accuracy on an image classification task, a result the researchers highlighted as proof that ternary computing is not just theoretically interesting, but practically usable for real artificial intelligence workloads. This was widely reported as the world's first carbon-based microchip capable of running AI tasks using ternary logic, and several outlets described it as a genuine leapfrog moment for post-silicon computing. To understand why carbon nanotubes matter here, it helps to know a little about the material itself. A carbon nanotube is essentially a sheet of graphene, a single layer of carbon atoms arranged in a honeycomb pattern, rolled up into a hollow cylinder roughly 1 nanometer wide. That is, thousands of times thinner than a human hair. Because of their shape and structure, carbon nanotubes conduct electricity extremely efficiently, and they allow engineers to build transistor gates that wrap almost completely around the current flowing through them, giving far tighter control than traditional silicon designs. For years, carbon nanotubes were mostly used in simple applications like battery electrodes, but researchers have increasingly seen them as one of the most promising materials for whatever eventually replaces silicon. The Peking University team's key innovation, the source gating transistor, works by extending one of the transistor's electrodes further into its own channel than normal. Designs allow. That extension creates a tiny controllable junction inside the transistor junction. Engineers can force the transistor into 3 distinct, stable electrical states rather than the usual 2. It is a subtle engineering trick, but it is also the exact kind of structural innovation that has eluded researchers trying to build reliable multi-valued transistors for decades. This was not an isolated project either. The same broader research group at Peking University had already made headlines roughly a year earlier for building a separate carbon nanotube-based tensor processing unit, essentially a specialized AI chip, using around 3,000 carbon nanotube transistors. That chip ran a 5-layer, convolutional neural network, achieved around 88% accuracy on a standard image recognition benchmark, and did it while consuming an astonishingly small amount of power, reported at less than 300 microwatts. For comparison, that is a tiny fraction of the energy conventional AI chips require to perform similar tasks. Together, these 2 projects show a consistent pattern. Chinese researchers are not just theorizing about post-silicon computing. They are actually building working hardware, publishing peer-reviewed results, and demonstrating real-world AI performance. China's carbon nanotube ternary chip is not the only ternary story making waves this year. Huawei, the Chinese telecommunications and semiconductor giant, has also been developing its own version of ternary logic, but through a very different route. Rather than using carbon nanotubes, Huawei filed a patent for what it calls ternary logic gates built using fully digital CMOS architecture, the same manufacturing approach used in most conventional chips today. Huawei's design maps electrical signals to 3 distinct voltage levels: 0 volts, 1.65 volts, and 3.3 volts, representing the 3 ternary states. According to details from the patent, Huawei claims this approach can reduce the number of transistors needed by around 40% while also cutting power. Consumption by as much as 60% compared to equivalent binary chips. Why does that matter so much? Because Huawei has been operating under heavy United States export restrictions for years. Restrictions specifically designed to block the company from accessing the most advanced binary chip manufacturing technology in the world. If ternary logic allows Huawei to achieve major performance and efficiency gains using older, more accessible manufacturing processes, rather than the cutting-edge lithography tools it has been cut off from, then ternary computing becomes more than just a scientific curiosity. It becomes a potential way around the entire chip blockade. Some analysts have gone so far as to call this a geopolitical milestone as much as a technical one, because it demonstrates a possible pathway for Chinese companies to compete in advanced computing without needing the exact same tools the West has restricted. Huawei's engineers reportedly describe their design as solving problems that even Soviet scientists could not fully crack back in 1958, largely because modern digital CMOS manufacturing gives them precision and consistency that simply did not exist 70 years ago. By mapping the 3 ternary states onto 3 very specific, carefully separated voltage levels, Huawei's chips are said to avoid one of the classic failure points of early ternary designs, which is signal drift, where the difference between states becomes blurry and unreliable as chips heat up or age. If that claim holds up under independent testing, it would remove one of the biggest historical objections to ternary logic ever becoming mainstream. It is also worth noting how broad the potential applications are. Huawei has pointed to AI data centers, autonomous vehicles, and machine learning systems as prime candidates for early ternary adoption, arguing that the technology could cut the computational cost of autonomous driving systems by roughly 2/3. Whether or not that specific figure survives real-world testing, the underlying logic is simple. Any industry that depends on massive, constant, the most from a system that needs fewer transistors to do the same job. And Huawei and Peking University are not the only Chinese teams exploring life beyond binary. A separate research group at Beihang University in Beijing, led by Professor Li Hongge, has developed a different non-binary approach called hybrid stochastic number computing, which blends traditional binary values with probability-based stochastic logic. This system was designed to solve two problems. Professor Li describes as the power wall and the architecture wall, essentially the same energy and compatibility issues limiting silicon today. According to reports, chips using this hybrid system have already moved into mass production for real-world applications, including touchscreens and flight systems in the aviation industry, with on-chip computing latency reported at the microsecond level. Taken together, these projects paint a picture of a country running multiple parallel experiments in post-binary computing at the same time, from academic labs to major corporations to state-linked manufacturing programs. That is a very different strategy from simply trying to catch up to existing binary chip technology. It looks more like an attempt to leapfrog the entire binary era altogether. It also reflects a broader industrial pattern that has defined China's technology strategy over the last several years. Rather than betting everything on one single approach and hoping it works, Chinese research institutions and companies appear to be pursuing several competing non-binary paths at once: carbon-based ternary logic, digital CMOS ternary logic, and hybrid stochastic logic, almost like running multiple experiments in parallel to see which one survives contact with real manufacturing constraints first. That kind of parallel, well-funded experimentation is expensive, but it also means that even if two of these three approaches eventually fail, the third might still succeed, giving the country several independent shots at the same long-term goal. Of course, it is worth being careful here, because breakthroughs like this often get wrapped in more hype than the science actually supports. Experts studying these developments have pointed out that scaling a laboratory demonstration into a mass-producible, commercially viable chip is an enormous jump. The world's first ternary computer, the Soviet Satan, worked perfectly well too, and it still lost to binary because of manufacturing and infrastructure reasons that had nothing to do with raw performance. Carbon nanotube manufacturing at the scale needed for mainstream chips remains difficult, expensive, and far from mature. Building a few thousand transistors in a research lab is one thing. Manufacturing, billions of them reliably, with consistent quality on flexible production lines, is an entirely different challenge, one that took the global silicon industry decades to solve. There are also compatibility concerns. The entire modern software world, every operating system, every programming language, every existing chip design tool is built around binary logic. Even if a ternary chip is more efficient on paper, integrating it global industry to redesign its software stack around three-state logic is a massive undertaking. Analysts covering Huawei's patent specifically noted that these remain early-stage results and that real-world performance at scale is still unproven outside laboratory conditions. There is a simpler way to think about the scale of this challenge. Every compiler, every piece of firmware, and every chip design tool used by engineers around the world today assumes a two-state universe. Rebuilding that entire tool chain around three states would not just mean designing new transistors. It would mean rewriting decades of accumulated software infrastructure that the whole industry quietly depends on. That is part of why even genuinely superior technologies sometimes take 20 or 30 years to some engineers remain cautious, even when the underlying physics looks promising. Cost is another factor rarely mentioned in the more excited headlines. Building a new fabrication ecosystem around carbon nanotubes would require enormous investment in purification techniques, since even tiny impurities in a batch of nanotubes can ruin a transistor's performance. Researchers have spent years just trying to grow carbon nanotubes with the consistency and purity needed for reliable, large-scale manufacturing, and while recent progress has been genuinely impressive, matching the near-perfect yield rates of modern silicon. Fabrication plants remains a distant goal rather than a solved problem. Still, the direction of travel is hard to ignore. This is not one lab publishing one interesting paper. This is multiple Chinese institutions, companies and different funding streams, all converging on the same basic idea within the same short window of time. Whether or not any single one of these ternary chips becomes the industry standard, the broader signal is that China is positioning itself to lead, or at the very least, seriously compete in whatever comes after silicon. And this timing is not an accident. As global tensions over advanced chip manufacturing continue, and as export restrictions on cutting-edge binary chip technology remain firmly in place, China has enormous strategic incentive to develop computing architectures that do not depend on the same tools and materials it has been blocked from importing. A three-state logic system, built from carbon rather than the most advanced silicon nodes, sidesteps that entire bottleneck. Whether by careful design or fortunate timing, ternary computing offers China a technical path that runs parallel to, rather than directly through, the chip restrictions imposed by Washington. Zooming out even further, this story fits into a much bigger pattern happening across Chinese technology research right now. It is not just ternary chips. China has also been racing forward in quantum computing, unveiling machines like the superconducting Zhuchongji processor, reportedly capable of outperforming the world's fastest classical supercomputers on specific tasks by many orders of magnitude, and the room temperature atomic quantum computer known as Hanyuan, which has already received tens of millions of yuan in commercial orders, including an international sale to a customer in Pakistan. A newer dual-core version of that same quantum system, called Hanyuan-2, was unveiled more, across two linked processing cores while running on less power than a typical home air conditioning unit. Whether through quantum bits, carbon-based transistors, or three-state logic gates, the common theme is clear. Chinese researchers are not simply trying to build a faster version of what already exists. They are testing entirely different foundations for what computing could become next, and they appear to be doing it across multiple unrelated fields simultaneously, from photonics to quantum hardware to fundamental logic architecture. If ternary computing does eventually scale beyond the laboratory, the implications could be significant. More efficient chips would mean AI models that require less electricity to train and run, which matters enormously as data centers worldwide struggle with power demand. It could mean smaller, cooler devices that do not need the massive cooling systems modern data centers currently rely on. It could reshape which countries and companies control the next generation of computing hardware, especially if it turns out that ternary architectures do not require the same ultra-advanced manufacturing equipment that binary chips currently depend on. Think about what that would mean for everyday consumers, not just data centers. Smartphones that run for 2 or 3 days on a single charge instead of one, laptops that never need a fan because they simply do not generate enough heat to require one. Wearable devices thin and cool enough to sit powered health monitoring. None of this is guaranteed, and all of it is still years away even under the most optimistic timeline. But it illustrates why engineers who have spent their careers immersed in binary logic are suddenly paying very close attention to a Soviet idea from 1958. But it is just as possible that, like the Seton before it, this new wave of ternary chips remains a fascinating scientific footnote, technically impressive, but never quite practical enough to displace the binary, around for the last 80 years. History does not always favor the most elegant solution. Sometimes it favors whatever already has the infrastructure, the investment, and the momentum behind it. And right now, binary still has all three. What we can say for certain is this: for the first time in decades, serious institutions, serious researchers, and serious companies are treating three-state computing as more than a historical curiosity. They are publishing results in major scientific journals, filing real patents, and in at least one case, already shipping products built on non-binary logic. Whether this becomes the beginning of a genuine post-silicon era, or simply the most sophisticated echo yet of a 1950 Soviet experiment, one thing is clear: the 80-year reign of zero, and one may finally be facing its first serious challenger. If you made it this far, you clearly love deep dives into the technology shaping the future, so do not forget to subscribe so you do not miss the next one. Thanks for watching, and we will see you in the next video.